Weight has a big role to play in how well the aircraft performs. The pilot's operating handbook is going to give you a lot of figures about what the maximum weights of the aircraft are. Maximum gross weight, max gross takeoff weight, landing weight, ramp weight, a lot of different maximum weights. For the Cessna 172, it's kind of the same weight for a lot of these figures. The 172 and a lot of the models that we're looking at, it's going to give you a maximum weight of around 2,400 pounds. Right? Anything higher than that, they really can't sanction any sort of operations. I guess you're in test pilot territory when you're flying over max gross weight. But weight has a big role to play in performance. A lighter aircraft, or an aircraft that's lighter than that maximum 2,400 pounds, like this one that's only 2,000 pounds, is able to produce the same, or I'm sorry, it's able to counteract its own weight. It's able to stay at the same altitude at a smaller angle of attack. It doesn't require as much lift, so its angle of attack can be smaller. Now, a heavier aircraft, one that's at its max gross weight at 2,400 pounds, in order to maintain that altitude at the same speed, it's going to need a bigger angle of attack. Now, what happens when you increase the angle of attack? You also have to increase the induced drag on the aircraft. So if you're increasing the drag that the aircraft experiences, that's either going to slow you down or it's going to require more power to maintain the same airspeed. More power means you burn more fuel, means you run out of fuel quicker. What's called your fuel endurance suffers, and your range, how far you can fly on a certain amount of gasoline, a certain amount of fuel, goes down. So it's less fuel efficient to fly a heavier aircraft. In addition to the maximum weight that you put into the airplane, it also matters where you put the weight. You can put the weight either aft or forward on the aircraft, and it's going to play with the performance, the balance, and the stability of that aircraft. Remember in class 1 we talked about the position of something called the center of gravity is going to affect the stability of the aircraft. You typically want it in front of where the lift is produced, but you don't want it too far back. You don't want it behind where the lift is produced in the wings, because that's going to lead to a less stable aircraft. So it really matters for both performance and safety where the placement of that weight is. So to give us an idea of where we're putting the weight and how to calculate that, we use a reference point. This is just kind of a arbitrary point on the aircraft. We think of it being on this axis of the aircraft that you see here, and the engineers and the manufacturers will just choose a point at random. On the Cessna 172, they happen to choose the reference point. It's called the reference datum. They happen to choose it right at the firewall, that area that separates the cabin from the engine itself, and that's our reference point. So we're going to call that like point 0 there. And then anywhere we put weight onto the aircraft, we're going to express where that location is based on how far away it is from the reference datum. So as you move backwards, as you move aft of that reference datum, you're counting up 50 inches, 100 inches, and so forth as you get to the tail, 250 inches. And then you can even see as you get in front of that reference datum onto like the cowling close to the propeller, it gets into negative territory, negative 25 inches, and so on. So to look at this, let's substitute the aircraft for a flat plane, this nice seesaw here. So basically the longitudinal axis of the aircraft can be thought of as a flat plane, and the point that we balance it on, the point that the seesaw sits on, can be thought of as the center of gravity. So in the most sort of simple explanation, if I take two equal weights, two 100-pound weights, and I put them on either end of the flat plane, either end of the seesaw, the point that's exactly halfway between the two of them is going to be the balance point. That's what's known as the center of gravity. So if you have equal weights, the halfway point between the two of them is where your center of gravity is going to be located. What happens if you take different weights and you put them on the seesaw though? So now there's a 100-pound weight, but then on the other side there's a 200-pound weight. What happens is the center of gravity is going to move closer to that heavier weight. So that heavier that weight is on that side, the closer its center of gravity is going to be to it. But think about it another way. What you're actually doing is you have a smaller weight that's balancing a larger weight. So that 100-pound weight, because it's further from where that center of gravity point is having the same effect on the seesaw as the 200-pound weight is close to the center of gravity. Even though the 100-pound weight is lighter, being further away from that pivot point, being further away from that center of gravity, gives it a greater turning tendency, what's called a greater moment. That's the ability of that weight to turn the seesaw a certain direction. So what this means is that if we know how much each one of these weights weighs and we know what position, in other words, what position relative to the reference datum we're putting these weights on the seesaw, we can calculate where the center of gravity is going to be located. So the weight we know is either 100 pounds there on the left or 150 pounds there on the right, and then we know the position on the seesaw. That position is called the arm. So that 150 pound weight is on the 25-inch arm, or the 25-inch station of the seesaw, whereas the 100-pound weight is on the 175-inch arm. All that means is the position on that seesaw that it's located at, or better yet, its distance from that 0-inch, that reference datum point. We know the weight and we know the arm of each one of these loads that we've put on the seesaw. Okay, math alert again. Here it comes, right? You knew it had to be another math thing with weight and balance coming into play here. So we can calculate, if we know the weight in the arm, we can figure out the moment. Again, the moment is that tendency or the ability of the weight to turn the seesaw, to turn the plane, to change the balance of the plane. So we'll start with the weight on the left. It's 100 pounds. That's the weight. The arm is 175 inches there. If I take the weight and I multiply it by the arm, 100 times 175, I'm going to get the moment, 17,500, and it's something called pound inches, right? Not too complicated. I took pounds, multiplied it by inches, I get pound inches. 17,500 pound inches on the left. Move over to the right. This is like a weigh-in for boxing or something. You have in that corner 150 pounds of weight at a arm of 25 inches. So once again, we're taking the weight times the arm and we're getting 3,750. So you have two moments. That's what I need to use to calculate that up, and I can use those two moments, 17,500 and 3,750, to figure out the center of gravity of this entire seesaw. And how I do this is I add up those moments, 17,500 plus 3,750, get the total moment of 21,250, and then I'm going to add up the weights. The total weight, 100 pounds plus 150, 250. Divide those now. 21,250 divided by 250 equals 85. That 85, that's the position of the center of gravity. So you can see there, if I move left on that ruler at the bottom there from 0 all the way to where 85 would be, that's the location of my center of gravity. That's the balance point between these two weights placed where they are on the seesaw, on the plane. Okay, you stuck with me through the math, so I'm going to give you kind of a funny picture just to illustrate this whole moment concept. So this isn't a tragedy for the aircraft. This is just something that happens when you get a fairly large snowfall at the airport. Basically, what you have is you have some heavy snow, relatively light. It's not the heaviest thing in the world, but it's weight. It has enough weight, and that weight is impacting far enough back on the aircraft. In other words, you have that snow falling on the horizontal stabilizer of the aircraft that's so far away from that reference datum that even though it's relatively lightweight snow, the arm is so large, it's so far away, it's so far aft that the moment is going to be big enough to be able to actually turn that aircraft. So you're going to come out in the morning after a snowfall and you're going to find some of these aircraft are going to be sitting with their tail on the ground like this. So when you're loading the aircraft, when you're trying to determine what you're putting into this airplane, the fuel, the people, the baggage, etc., the equipment, you want to make sure that that center of gravity is in the right place. So what's that right place? Well, I said it before, the center of gravity should be in front of the center of pressure. You can refer back to Class 1 aerodynamics on this, but the stability of the aircraft is based on that center of gravity being in front of where the lift is being produced through the center of pressure. This is typically around the midpoint of the wings. So the center of gravity being in front of that is going to add to the stability of the aircraft. In addition, in a tricycle geared aircraft like the one here, the 172, and a lot of the aircraft that you're going to be flying, the center of gravity is going to be in front of the main gear. So this is the goal of weight and balance. This is the goal of loading an aircraft properly, is getting that center of gravity in its proper place. How we make sure we're loading it properly is going to be helped by, again, going into the pilot's operating handbook. This time it's section 6, the weight and balance section. This is going to have all the data that you need to figure out if you put certain weights in certain positions on the aircraft, will you be loaded properly or will you not be loaded properly, and will you be within that or less than that maximum allowable weight. In order to calculate this, we need a starting point. We need to know how much that aircraft is going to weigh before we start putting things into it. So what we're looking for is something called the empty weight of the aircraft. The empty weight is a very specific term. It means something very, very specific. So we want to be careful about terms here. The empty weight includes the airframe and the power plant, all the permanently installed equipment, anything that's basically nailed down inside the aircraft, and it also includes all the non-drainable fluids such as unusable fuel and oil. What's unusable fuel? Basically, you have a fuel tank capacity of, let's say in a standard 172, 43 gallons. Now, part of that is considered usable. In the normal course of operations, you're going to use that fuel. Part of that fuel is going to be considered unusable. What does that mean? It means that you have to allow for the possibility that even though you're taking 43 full gallons of fuel on board, you're not going to be able to use 3 of those gallons. The reason why could stem from surface tension inside the tanks, uneven drainage, the fuel not being able to be carried by the ports inside the wings. Basically, think of this really simple concept. If you have a cup of coffee and you drink that coffee all the way down, you'll have drank all of the coffee that you can use, but if you look inside the cup, there's still going to be a little bit of that coffee left over in the cup. That's like your unusable coffee. Well, it's the same thing with fuel. You have an unusable portion of fuel and an unusable portion of oil. That's going to be incorporated into the empty weight of the aircraft. So we don't have to think about that when we start adding fuel and oil into the aircraft later. So how do you know what the empty weight of the aircraft is? One of the legal documents that has to be on board the aircraft is a certified weight and balance report. So you see this here, the aircraft owner, in this case Freeway Airport Incorporated, for this particular aircraft is going to certify the empty weight and balance. And they know this because they were the last party, they were the last guys to either take things out of the aircraft or put things back into the aircraft. So every time you take things out or put something back in, you have to update the empty weight and balance to, okay, this is what the aircraft now weighs, and this is the position on the aircraft that all of those weights are operating through. It's basically like the empty center of gravity. So in this report, it's showing an empty weight of 1,492.5 pounds and an arm of 39.5358. It's really specific, right? You multiply those two together and that gets you your moment of 59,007.23. So this is our starting point, and then we're going to start loading things up into this empty aircraft. So now we know the empty weight and balance of the aircraft before we start putting things into it. So over on the right there, we get a little bit of a table going. Down the first column, we've got each item, starting with the basic empty weight, and then on the right, we have the weight, the arm, and the moment. We're going to find each one of those things for all these other things we're going to load onto the aircraft. Let's start with usable fuel. So for all of the things we put on the aircraft, we're going to look at another page of the POH in section 6 for how we treat that stuff. So if you look at the page there, that's excerpt on the left, you notice that in note number 1, it says the usable fuel center of gravity arm for standard long range and integral tanks is located at station 48. Okay, what that means is that no matter how much or how little fuel you put into the aircraft, it's going to be at the same arm. So if you know how much weight you're putting into the aircraft, you know the arm is always going to be 48. So we can take the weight and the arm, figure out the moment. So a standard tank for a Cessna 172, and again, you can look elsewhere in the POH for this number, is 40 gallons of usable fuel. Now, gallons is not a measure of weight. Gallons is a measure of volume. So we need to know not how much in terms of volume, we need to know how much in terms of pounds we're taking onto the aircraft. Well, it so happens that we know that a gallon of 100 low lead fuel, which is what we're putting into the aircraft, weighs 6 pounds. So I'm taking 40 gallons of fuel. That's going to equal 240 pounds of fuel at station 48. So we'll get that into our table there on the right. 240 pounds at 48, multiply them together and you get the moment of 11,520. Okay, now let's start adding payload, the people and baggage that we're going to put onto the aircraft to get from point A to point B. So where you put the people and the equipment, or the people and the baggage in the aircraft, is going to play into what the balance of the aircraft is as well. So we'll start from the front and start moving back. There's the front two seats, the pilot and the front passenger. And you notice there on the diagram that it has the number 37 in there. That says that that arm of those seats is 37, but there's also an asterisk, and then in parentheses it says 34 to 48. What that means is that you can slide these seats forward and backwards, right? You know, bigger people are going to need to crank that seat back a little more to give themselves a little bit more legroom. What that means is that the arm is actually going to move backwards at that seat. But 37 is kind of a nice compromise, so we'll stick with that. And let's just throw out some numbers. Let's say that we've got 300 pounds of humanity up front, maybe a pilot who weighs 150 pounds and a passenger who weighs 150. And they're both at 37 arms. So that goes into our pilot and passenger line on our table, 300 pounds at 37, multiply them together and get 11,100 for the moment. Move back into the back seat, our rear passengers, let's just say we have one 150-pound person, but that person being in the back is going to have a greater moment because that arm is longer, right? It's further away from that reference point. It's at 73 inches instead of 37. So rear passenger line there in the table, 150 pounds times 73 gives you a moment of 10,950. Half the weight, but almost the same moment as the front two people. And finally in the rear we got baggage. We'll say we got 50 pounds of bags, and that, as you see in the diagram there, is going to be 95 inches. That's the arm. So multiply those together and you get your 4,750. So now we've got all the weights, the arms, and the moments. What's next? And the next step is just to add them together. So you can add up all the weights to get the total weight of 2,232.5 pounds, and then the total moment, adding those up, is 97,327. Those numbers don't mean a whole lot to us yet, do they? So we're going to need another page out of the POH to help us tell us what does this mean for our flight. So this next page in section 6 of the POH is the center of gravity moment envelope. So we'll take those numbers that we computed before, that total moment and that total weight, and we'll find where they are on the chart there. So starting at the bottom, the horizontal line at the bottom, the moment line, and they do you a favor and they kind of divide by 1,000, so you're not dealing with massive 5-figure numbers at the bottom, just 2-digit numbers there. But where that line is for 97,327, that's going to be our line for the moment. Now, going from that vertical line all the way on the left, we're going to use our weight that we calculated, that 2,232.5 pounds. Take that line and draw it across. Now, the intersection of those two lines, that's going to show us if our center of gravity is inside what's considered the normal category for the flight or the utility category. What those mean, remember when we were talking about the category and the classes of aircraft, the different things that you can get away with, the different maneuvers that you're allowed to do are going to be listed in somewhere else in the POH, section 2. So if you're in the normal category, that's sort of your basic run-of-the-mill maneuvers. Your utility category will allow you a little bit more freedom to do some maneuvers. So maybe things like spins are approved only if you're in the utility category. In other words, only if you're light enough and your center of gravity is far enough forward. But in any case, if we're just trying to see if our flight is within the acceptable limits, within the safe limits, normal category is going to be just fine. So there we are, smack in the middle of the normal category there. The center of gravity is really ideal for the flight. If we want to visualize this, though, we can still use that same diagram that we used before. So the center of gravity in terms of numbers here is just the total moment divided by the total weight, right? We did that before in the example before we started getting into the actual weight and balance. Total moment divided by total weight gives us the center of gravity. So we do that division, we get 43.6 inches. I can actually place that on the aircraft, and you notice there, and this is all to scale by the way, this diagram, that center of gravity is going to be located just in front of the center of pressure. So we have a very nicely loaded aircraft where the center of gravity is not behind the center of pressure, but it's not so far in front of it that the aircraft is going to require a ton of like tail down force and angle of attack to keep it flying at altitude. So this is a very ideal loading for the aircraft. This brings us to the end of airplane performance. There's a lot of material in this class. Congratulations for sticking with it. But the reason that there's so much here is because it's a really broad topic, right? We're asking that initial question, what affects how well or how poorly the aircraft flies? That's a huge question, right? And that gets into the conditions that we're flying in, what we've put into the aircraft, the weather, the air density, temperature, et cetera, et cetera. A lot of stuff going on. So hopefully we've gotten the concepts out of the way. These are what makes the aircraft fly better or worse, and how do we calculate that? Because what we're building slowly and slowly up to is at the end of the course here, we're going to put it all together and we're going to put together a cross-country flight, and we're definitely going to want to know what our takeoff, landing, and cruise performance is going to be so that we're making sure that we're conducting that flight safely. So we will definitely review a lot of these concepts going forward as we get up to that final goal of putting the cross-country together. The next course is going to deal with regulations. So we're going to dive into the federal aviation regulations. We're going to sort of put our lawyers' hats on and look at all the rules of the road, so to speak. So we'll see you back for Class 6 regulations.